It's a great pleasure to be here, and as mentioned, we're going to talk about 3D printed tracheal splint we've developed to treat Tracheal Malaysia, but I'd also like to put it in a more general context of why do we need to use 3D printing for medical devices, for surgical reconstruction, and some other applications, and some of the challenges we face in translating the technology. So in the talk today, I'm going to first explain the need for 3D printing or 3D printed devices in reconstructive surgery. Then I'm going to, as an example, show our work on the tracheal splint to treat collapsed trachea mainly in kids and some adults as well. And then conclude by talking about some of the barriers we face in translating this technology for custom reconstruction in a few different areas. So I think there are two primary reasons why we'd like to use 3D printing in reconstructive surgery. One is often in reconstructive surgery you face very low volume markets. There may be less than 2,000 patients a year. That's especially true in pediatrics and a lot of really complex cancer reconstructions. It's just, in some ways it's fortunate, of course, but there are not enough patient volumes to make it economically feasible for a lot of medical device companies to get into this space, and lower markets from a manufacturing perspective mean higher cost per device. The other thing is that these markets, reconstructive surgery, often present very complex and variable anatomy. That means it's not like your typical one-size-fits-all medical device. You really have to, in these cases, customize the device to the patient. We know, obviously, in pediatrics, kids come in a wide variety of sizes, and you really have to customize the device to their anatomy. And also, you can imagine if you're doing complex tumor resection and you're trying to reconstruct the defect that's left behind, that can be really complicated geometry and anatomy to fix. And the other thing, of course, if the device is more complicated, that also makes it much more expensive per device to manufacture. And that's why you don't see a lot of medical device companies, and I understand completely, pursuing this market. And even from the point of view of trying to spin off companies, it's very difficult because it's hard to get funding, when you have a low market. And this was really highlighted in a New York Times article about 6 years ago now about medical devices for children, saying that really the development of surgical tools and medical devices for kids lags about a decade behind that of adults, really due to the economic factor. So I think eventually going forward, if we can utilize the technologies I'll talk about, my personal opinion is that we'll see sort of more point-of-care manufacturing, which means you'll see more manufacturing done at academic medical centers and so forth. So this is ideally what we'd like to do. We'd like to be able to have a physician come to us with a clinical need, use data from the patient, CT scans, MR scans, other information to create a model of the patient, and then design the device for the patient and actually simulate the device computationally before we implant it in the patient. And then we like to be able to use 3D printing with a variety of biomaterials, although this is a limitation right now, to actually build the device. And we can actually also, in the whole suite of efforts, build the device, make a model of the patient to practice the surgery on, and make guides for the surgery to make it a truly personalized reconstructive surgery. And really, when we think about it, there are two developments probably in the last 15 to 20 years that have made this pathway a viable or feasible pathway. First of all, as you see here, we have a lot of software now that we can readily take patient information like this CT scan. We can build a digital model of the patient. We can design the device, and we can actually digitally size the device to the patient. And we can actually perform simulations on the device to make sure that it meets our design requirements. The other thing, of course, is if we would have to rely on traditional manufacturing techniques to build these devices, it would be very difficult. So the advent of 3D printing, and 3D printing, people don't realize, has been around since the mid-1980s. It's just that you see a lot of printers on Amazon because they came off patent. But 3D printing gives us two advantages for this application. One is that With increasing complexity, as shown in the red line, the cost per device in 3D printing doesn't really go up that much. Whereas in traditional manufacturing, there actually reaches a point where you can't even make the device. The other thing is that with 3D printing, the cost per device, whether you're making one device or you're making 1,000 devices, is pretty much flat. So that means if we have a niche market in which we need to make maybe 10 or 20 devices, our cost per device is much lower than in traditional manufacturing like injection molding, where the costs go up exponentially if you want to make one device. So if you had to make, with injection molding, only one Coca-Cola bottle would probably cost you $10,000 for a 2-liter bottle of Coke. But since they can injection mold and make millions of these, it costs you pennies. So these are the really two advances: the ability to design from patient image data and to use that data to manufacture 3D print from biomaterials has made this sort of reconstruction feasible. So the example I'm going to talk about today is that of Tracheobronchial Malaysia. It's just a fancy word for meaning soft trachea or airway that collapses upon exhalation. And this occurs in kids because they often have associated cardiopulmonary defects. They have things like aortic rings, and these restrict growth of the airway. And we believe that your airway is actually made out of cartilage rings, and this prevents normal development of the cartilage rings. Those are what give stiffness to your airway and prevent it from collapsing when you exhale. So if you don't have these, on exhalation, your airway can completely collapse. So our idea, a proposed solution, you could either put a device inside the airway, that's called a stent, like artery stents, or you can put a device around the airway to hold it open. Stents have a lot of issues, especially in kids. If you make them out of metal, they erode through the airway, or they migrate, or they prevent mucus clearance. So even though it's a more invasive procedure, we felt that making a device around the airway, you still implant it, is a better way to open up the airway. So following that concept of using patient-specific data, creating a device, simulating how the device will behave and see if it meets our design requirements, and then actually 3D printing it, this is what we do to make the tracheal splint. This is actually a CT scan or a model of the patient that was done here in Atlanta. You can see this is the trachea. It goes down and splits into the main stem bronchi that go to your lungs. And this right main stem bronchus, this is actually the lumen or the airway itself, is almost completely collapsed. So then we can actually design devices and digitally match them to the patient. As seen here, we can perform simulations to make sure they have the right mechanical properties to withstand the forces in the airway. And then when we're satisfied with the design, we actually build it using a 3D printing technique called laser sintering, which means that you basically take a laser, you have a powdered material, it sweeps that powder into the build area, which is shown here. And you might be able to see they're a little bit faint, but there's some dark lines here. This is actually the outline of the device as it's made by the laser beam. So the laser beam traces the design in the powdered material and melts it together. And then because you have a bunch of loose powder around, it sort of keeps it up. Because in 3D printing, you can imagine if I'm printing my arm and I have nothing to support it, it's going to collapse. But in this case, there's a lot of loose powder, and that sort of basically keeps the overhanging structures up. So the nice thing is we can build about 200 of these devices in about 4 to 5 hours. This is what they look like. This is actually a 3D printed model of the patient's airway, and you can see how the devices fit around the airway, and these holes are to run sutures through the wall of the airway and pull it open, much like if you think of an analogy, think about a tent that's collapsed, that's the airway. The tent stakes are the splint, and then the ropes are the suture. So you pull the tent through the tent stakes, and it opens up, and that's what it does for the airway. And then we perform actual testing as well to make sure it meets our design requirements. So I started doing this work. I was at the University of Michigan up until 2 years ago when I moved to Georgia Tech. I continue to work with Michigan, and they've done a implanted this device in about 20 patients so far with Tracheal Malaysia. The first patient we did here in Atlanta, especially have to acknowledge clinical colleagues, Steve Gowdy, Kevin Marr, Dr. Subi, she's a cardiac surgeon, I can't pronounce her last name, and April Landry. They were the clinical team we worked with to actually develop the splint for the patient here. And this is very successful. The child has gone home for the hospital. This was actually a unique case we did with Penn State. This child was born without a trachea. This is called Tracheal Agenesis. It's very rare. So basically in this genetic condition, the bronchi are actually coming off the esophagus. So there's no trachea, and what the surgeons do is they actually take the esophagus and make that into an airway, and they bring it out the neck. So to our knowledge, no child has survived with this condition probably past the age of 8. We're hoping that this case will go better. So they essentially, at Penn State, they brought the esophagus out through the neck. But the esophagus is very pliable, as you can imagine, to swallow food. It doesn't have the mechanical properties to withstand breathing. So they used a splint, and we made a curved splint to help keep the esophagus open. And fortunately, that child has also been able to go home from the hospital now. So we're now at about 21 patients, and all of these have to disclaim that this is an investigational device. It's not approved by the FDA. We get clearance under the FDA Expanded Access Program. So if you don't like blood, look away, but fortunately you have a little bit of time before lunch. But this is actually the first 3 surgeries that were done at the University of Michigan. This brown is actually the patient's airway. You can see this is the device design. It's basically, crack open the chest. They do put the kids, if they have associated cardiac conditions, they put them on bypass. And you can see this is actually our second case where we made 2 devices they implanted, and we could make changes in the device to allow the devices to be put at basically the carina, which is where the mainstem bronchi branch off. And we sat down with the surgeons on a Wednesday, we designed this on a Thursday, and we built it on a Friday. So you can make a complete de novo medical device in basically 3 days. When we and also the FDA, we look at what are the clinical outcomes we expect from the device, and what are the risk of the device, and what are we worried about. There are 3 major things. One, obviously we want to create a patent airway or an open airway so the child can breathe, and we want that patent airway to last over time. We believe in this particular condition that as the child grows, the risk for collapse lessens. So if we can get the kids out about 2 years post-surgery, that they should be fine. The second thing is we're putting a device, a structural device around the airway. We don't want to interfere with growth of the airway, because if we constrict growth of the airway, that will inhibit or retard lung development to some degree. So we designed the device to allow growth of the airway, and that's a very important thing in pediatric devices. And we actually use a resorbable material. So this material will last about 3 years in the body, and then it will resorb and the child will excrete it. There's no need for a second surgery, which is an advantage. So those are the 3 things that we want to really track in these kids. And if you look at the top, this is a CT scan pre-op from a couple cases. And what you're seeing here is that because the airway and the lungs are filled with air, that shows up as a dark signal on the CT scan. So if the airway was patent, you'd see a completely continuous dark line from the top here into the lungs. And you can see there's brief, there are interruptions on exhalation. So that means when the child is trying to breathe out air, the airway is collapsing and the air is trapped in the lungs. And many times they go into respiratory arrest. Immediately post-op, you can see that now these application of the splint, that these airways are continuous now. So we could show in a follow-up of 15 patients that this is a ratio we look at in terms of if it's less than 0.5, that means the airway is collapsing, and 0.6 to 0.9 is normal. Pre-op, it's not normal, and post-op, it's normal. The other thing we wanted to track is, does the airway grow normally over time? And this is the first patient that was done in Michigan. This is the untreated size of the untreated bronchus in black here, and the untreated bronchus in red and the treated bronchus in black. And you can see that the treated bronchus grows at about the same rate as the untreated bronchus. The last thing is, we really want to see, does the device actually go away with time? This is a little bit of interpretation, but this dark signal on MRI is the device around the trachea at 6 months, and then at 12 months, and then 3 years and 4 years. And what you see is that you see some breakup in the signal as shown by the arrows here, and that means the device is going away over time. So we could show that the device basically fulfills its physical clinical outcomes in that it provides an open airway, it allows the airway to grow over time, and then the device is going away over time. But of course, the really important things is, does the device contribute to the patient's and the child's quality of life? And we look at this based on most of these kids prior to surgery are chronically hospitalized. That means they never go home. The second patient was in the hospital for the first 16 months of his life, connected to a mechanical ventilator. We could show that all but one went home post-surgery. The other thing is, as I mentioned, most of them are on continuous mechanical ventilation. They have a hole with a tracheostomy, and they're connected to a machine to help them breathe. And some are on ECMO, which means you don't breathe at all. They circulate your blood through an oxygenating machine, and you can live about 2 weeks on that. And most of the patients were on at least continuous ventilation. Some were on ECMO, but post-surgery, most of them could come off. So we believe also that, that this device is helping these kids on the road to recovery. Again, apologize for sort of a bit of a bloody slide, but this just shows that we're trying to take this technology and apply to other reconstruction applications. So as you can see, we're interested in a lot of head and neck reconstruction. This is ear reconstruction we're doing with a colleague at Michigan. This is the device with holes in it. This is the printed device. This is actually the device in a rat. So this is not a human ear, but you can see that we have holes in the device so we can get tissue and cells to grow in the device. This will actually go away over time, resorb, and we hope to have a normal ear. Doing the same thing with noses and with the same colleague. And here we're doing work on reconstruction of the mandible in kids. There's some conditions where kids don't have normal TMJ joints, and we could make an exact design from the mirror image of that joint, and we make a collar to fix it to the remaining part of the mandible, and you can see reconstruction. This is an animal model post-surgery. So we think that this is really a platform technology. We can use it to design a lot of different devices for kids, for adults who have very complex defects due to tumor resection. However, in some ways to us, the technology is the easy part. The other stuff around is the hard part. And we face a number of challenges of getting this into translation. First of all, as I mentioned, if you have small market sizes, it's just the way of the world that for medical device manufacturers, they have to sell devices to stay in business and to create health solutions for all of us. And for these markets, it's very difficult to commercialize technology. So in some ways, we're trying to take this technology directly from the university and go into patients. Universities aren't really used to that. Medical devices bring a lot of liability, and I understand that. And that's a very difficult thing. For example, at Georgia Tech, we can't actually produce devices on campus because of liability. We have to produce them off campus. And I think this is an issue we really have to look into, a way to address these issues. Michigan did it in a limited sense. They have a medical center, they have their own insurance, but this is to enable us as academics to move this technology into patient use. We have to solve this problem. The other thing, of course, is the regulatory environment. We're all interested in creating devices that are safe for patients and effective for patients. But you can imagine that we are making devices for maybe 10 patients a year or 100 patients in a given market. We have quality systems we put in place, and we do a lot of preclinical testing. But running clinical trials for this amount of devices becomes very difficult. Running a clinical trial, for example, for 15 patients with the Splint device, we estimate would cost $8 to $10 million. And it's very difficult. Again, it's a capital issue of trying to raise money to get these devices into clinical trials. We also face some technical issues of 3D printing with a broader range of materials and implementing quality control for medical devices. But I would say that the top two non-technical issues are some of our biggest obstacles. So I think what I wanted to show today is basically that by combining image-based design, using patient image data, combining that with 3D biomaterial printing, we can actually create custom devices for pediatrics and cancer markets to personalize it for your reconstructive needs. So in many cases, what surgeons now do to reconstruct complex defects in the head and neck is they take a piece of your leg bone and they cut that up and they transplant that into your face. So in that case, you really hope your surgeon is not only a talented surgeon, but they were an art minor in medical school, that they could really design it well. So we're trying to take those issues out of it. We've showed that we could do this with an example of the Tracheal Splint. We've had some success in 20 patients in whom we've implanted 40 splints. We face a number of challenges in terms of implementing quality control because, as you can imagine, these devices change for each specific patient. And of course, I think our bigger challenges are sort of around liability. How do we address liability and get these devices into patients? And working with the FDA, can we find a regulatory path that keeps patients safe but is economically feasible for us to translate these devices into clinical use? And with that, I'd like to acknowledge many of my clinical colleagues I've worked with, especially Sarah Jo Kratz and Harsha Ramaraju, who worked a lot on the quality and the Splint cases and the funding of the NIH. And if we have any time, be happy to answer any questions. Thank you.